Welcome to the lecture on stochastic calculus. So in this video, I would like to start chapter 2, which is on continuous time stochastic processes, in particular on Brownian motion, which is maybe the fundamental building block of the theory we're going to develop in this course. And in this video, I would like to start giving you the definition and first properties of the Brownian motion. So let me quickly again formulate what's the general theme or general aim of the second chapter, which is called Brownian motion and local martingales. So what we want to study are the stochastic or continuous time stochastic processes, which will allow us to develop stochastic calculus. So in particular, stochastic integration and solve stochastic differential equation. Okay, so general aim is study continuous time stochastic processes. But before we can really focus on the Brownian motion and the continuous time stochastic processes, I would like to make some general assumption for the course and to recall or provide you some definition which are used all the time. So just to fix some vocabulary right from the beginning. The first thing I would like to assume, which is the standing assumption for the whole course, is that we always work on a suitable underlying probability space, which you want to assume that it's completed. So we work on suitable. So you might recall from previous courses in probability theory that you need always to find a suitable stochastic basis where you can define random variables and all the random objects you want to have. But I believe now that you are able to do this. So I'm not stating it that there's always an underlying probability space which allows us to find all the stochastic processes we want. And suitable means for us, we want to assume that it's a complete probability space. And what does it mean? This means our sigma algebra F contains all sets with measure, probability measure, so with probability 0. So we assume that all the null sets are included in our sigma algebra as well. And secondly, we want to assume that we have terminals, her time horizon, so the number capital T is something which is strictly bigger than 0 and greater or equal to infinity. So we allow that the terminal time, let's say, is really infinity, because in probability or in stochastic calculus, you also care about the long-term behavior of stochastic processes, which will not be the part of the lecture, but many of the results and definition we give here, they work equally fine for t equal to infinity. So this is just for a completeness reason because it doesn't matter for us. I will make it explicit when I want to assume that t is finite. Okay, so these are the general assumption. And now I would like to, as the first thing, I would like to make my life a bit easier by introducing two conventions. The first one is I want to assume, I want to define. So if I look at the interval 0 to t, I want to define this to be equal to 0 infinity if my time terminal t is equal to infinity, right? So I allow to include infinity, but if I do so, I don't want to have it as like a extra time instance. So I'm looking at the half open interval 0 to t. That's 0 to, yeah, if t is equal to infinity. All right, and then just to be clear for one, so if I look at two random variables, so variables x and y, and I write x is equal to y, what do I mean? Well, this means x is equal to y almost surely. So I mean, we work on a probability space, so all equalities and inequalities, they work in a almost sure sense, but I might not write it all the time, right? Because otherwise I have to write it every line and almost surely, which gets a bit annoying over time, right? The same for greater equal or lesser equal, right? Okay. Okay, so these are just to make my life easier to state it once in a correct way. So we have always an underlying probability space, and all the equalities and inequalities are considered as in an almost sure sense. Okay. So far, so good. And now I would like to recall or fix some terminology which you might have seen already if you have have done like other courses like mathematical finance or Wahrscheinlichkeitstheorie 1. But for those who haven't seen it, I want to like go through these terminologies. They're just simple definitions which you need to, well, yeah, get used to. But don't worry, over time you will get used to it. So okay. Okay, first thing I would like to tell you is, okay, what is the stochastic process? Right? So we used the word already several times, but now it's, I think, time to state once what we actually mean by stochastic process. So a family of RD valued random variables, and the family is indexed by this set 0 to capital T, is called stochastic process. Right. So nothing special. A stochastic process just means you have a family of random variables indexed with time, I usually say. So the index set is 0 to t. And this terminal t set might be infinity. Okay. Okay. Then, if we have a stochastic process, well, what we can do is we can fix an omega. Oh, and this works for almost all omega. And then I can look at the map, which maps time. So I freeze my omega, and then I have a function acting on the interval 0 to t and maps to RD. And the map is naturally given by t maps to the random variable xt at the fixed, evaluated at the fixed omega. And this is then just called a sample path. Right? So I sample the process, means I choose one omega, and then I look at the trajectory in time, which is my path of, oh. Okay. So this is what I want to call from now on, or have already called, sample path. Okay. Next. If I have now stochastic process, I want to have some regularity properties of the stochastic process as well, which refers to the sample path of the process. So if I say a stochastic process is continuous or right continuous, just means the sample paths are continuous or right continuous in the usual sense, because these are then functions from time, from the interval 0 to t to rt. And there you know what continuous means and what right continuous means. Say x is continuous, or right continuous if, well, the sample path is it's the sample path of this process x are right continuous, continuous or right continuous. Of course, this only holds in an almost sure sense, as everything if you work on the probability space. Okay, so that's what I mean by continuous process or right continuous process. Just refers to the sample paths. Okay. Okay. This is okay. Now we know what a stochastic process is, what the sample path is, and what this means continuous, right continuous. Okay. So let's come to filtration, which you might have already seen as well. Okay, so what is the filtration? Family of sigma algebras F, which is also now indexed by a time interval 0 to t. And we assume, this is part of the definition, that these sigma algebras are all sub-sigma algebras of the given one on the probability space F. And I call this family called filtration if they're increasing or non-decreasing. Right? So if I have a sigma algebra at time s, it's included in the sigma algebra at time t if for s t okay, so this is sigma filtration. Here we go. Okay. Okay, so this is my filtration. If I've given a filtration, I can define what a stopping time is. Okay. So I'm just running through a few definitions, but don't worry if they if you haven't seen it. I mean, they will come up rather recently, quite frequently, so you will get used to them and familiarize yourself along the way. So a random variable tau. So what is it? It's, as every random variable, is acting on the probability space, so on the sample space omega, mapping from the reference to 0 to t, and I'm allowing stopping time to take the value infinity, is called stopping time. So when the stopping time is always with respect to given filtration, the filtration okay is ft if the event tau being less or equal than t is ft measurable. So this means at time little t, I can decide whether I should stop with respect to the stoppage time tau or not. Okay, so this is what I would like to call a stopping time. Okay. And if I have, again, given a filtration, last definition, before we really start talking about the interesting objects here, is, okay, what it means for a stochastic process to be adapted. So x t is called ft adapted if x, so x at the point t is ft measurable. Okay. So these are all like terms which will pop up from time to time in the course, but I mean there's nothing deep behind them. It's in their common terminology, and I would like to ask you just to familiarize yourself with these terminologies, so that we can focus on the mathematical part and not on the language. Okay. So let's come to the maybe the main object, or the most frequently appearing object in this course, which is Brownian motion. So let's come to the start of this subsection. On Brownian motion. Okay. Okay. So first thing I need to give you is, what do I mean with the when I say a stochastic process is called Brownian motion. Okay. So let's come to definition 2.1. So the numbers I use here in this lecture corresponds to the numbers in the lecture notes, so that you can follow them also on the lecture notes. And also, if I use short writing, so might be a bit brief, then just look at the lecture notes where I fully formulate everything in a hopefully correct manner. So real valued stochastic process B T is called Brownian motion if the process had the following properties. So sometimes one is, what can we say? It's a one-dimensional Brownian motion. Of course, there are multi-dimensional extensions, and so this is, to be precise, is a one-dimensional standard Brownian motion, what I'm going to define. But here in the course, we will just call it Brownian motion because we are not considering the objects. So I call a process Brownian motion if the following four properties are fulfilled. First property I would like to have is that my stochastic process B starts from 0. So at time 0, it's constantly equal to 0. Second property I would like to have, x that B has independent increments. Okay. So what does it mean? If I look at time t0, right? So the increment from B at time 0 to B at time t0, and then from t1 to t0 and so on. So from Tn to Tn minus 1, these are independent random variables. And so here, these t's are just 0, 1, and up to time Tn. Right? So what if I look at the increments of this stochastic process, what I see is they form independent random variables for any partition I take here. Okay, so what's the third property? The third property is B has stationary and normally distributed increments. Okay, this is a long statement. What does it mean? So it doesn't matter at what increment I look. So if I look at from the increment from S to T, this is normally distributed with mean 0. And the variance is just given by the time increment from S to T. So ST. Yeah. So this means stationary here means, okay, if I look from the increment from 0 to 1, and then from 1 to 2, they have the same distribution, and the mean is 0, and the variance in this case is 1, because they have a time increment of 1. And the last property, I want that it's a continuous process. B has almost surely, so of course this is again almost sure inequality, but I will drop it in the future. Continuous sample path. Okay. So these are my 4 properties. I would like to have my process if I want to call it Brownian motion. So Brownian motion fulfills these 4 properties. So let me show you how a Brownian motion looks like if one samples it. And you are invited to produce or sample your Brownian motion yourself in one of the first programming exercise, right? That you get a feeling how Brownian motion looks like. So what do we see here? We always start at 0. This is 0. And then I have continuous sample path, and the probabilistic properties, okay, they are hard to see. So these are 5 sample paths or realizations of a Brownian motion. You can amuse yourself to produce more. So this is really the rough process. And if you recall my first motivating application of stochastic calculus, namely math finance, you might remember that we wanted to have rather rough objects in order to model price processes. And you can have a look at this price trajectory of some stocks, and you will see, I mean, they look also rather rough. And so you might find it natural to take the Brownian motion as a starting point to do financial modeling. But this is not part of the course, but just to give you a flavor where it is used. Okay, before going on, let me give you some remarks regarding the Brownian motion. Okay, so the first remark I would like to point out, okay, there are many definitions of a Brownian motion which are all equivalent. So if you have seen a different definition in some previous courses, you might want to convince yourself that they're actually equivalent, which I would expect. So there are, and also we will see along in this course some other equivalent characterization, which one could equally well use as a definition. There are various ways to define Brownian motion. And as you might know, is okay, I have here a wish list of properties which I want my Brownian motion to fulfill. That's a nice idea to create a wish list, but if you want to do it mathematically rigorously, you need to construct that ensure that such a stochastic process really exists. And this, of course, can be done. It's unfortunately not part of the lecture here. What you can look up in some probability books. And the first construction actually of such a stochastic process with these 4 properties, so of Brownian motion. So let me use the short writing. And so BM, okay, we will use it often. So short BM was provided by Norbert Wiener. And this means Brownian motion. It means not, but this in his honor, Brownian motion is often also called Wiener process. Yeah, so if you see a process called Wiener process, a stochastic process called Wiener process, it is a Brownian motion in our sense. Okay, and my last remark, why the Brownian motion is so important and a universal object in modeling of real-world phenomena, is that it can be considered as a functional version of the central limit theorem. Brownian motion of the normal distribution in the sense of so can be considered as a functional version of the normal distribution. So what does it mean? If you, for example, take a random walk and scale it in time and space in the correct way, the limiting object will be a Brownian motion. And this is, if you have seen it, this is part of what's called Donska theory. So theory. Okay. And this is also not part of the course. It's just a side remark why the Brownian motion is such a universal and omnipresent object in stochastic calculus. Okay. All right. So let's study a bit. Actually, the filtration generated by a Brownian motion. So if you recall, if I have a stochastic process, every stochastic process, and this is not special to the Brownian motion at all. So let me take a general stochastic process xt, generates filtration. Which is usually denoted then fx t by setting. And this is the minimal filtration you need in order to make the process x to be adapted. Right, so this is the filtration generated by all the random variables xs for all s lesser or equal than t. Right? And this is right? If you want to spell it out, this is sigma algebra generated by all the pre-images of sets A under the random variable xs, where A is part of the Borel sigma algebra, and R, or RD. Okay, let's keep it one-dimensional, and S in no, small t. Yeah. So just, and this is standard notation here. So this is Borel, the Borel sigma algebra. On R. Yeah. So this is just the minimal filtration you need in order to ensure that X is adapted. Okay. And this filtration is called the natural filtration of X. Let me. Yes. Okay. Is called natural filtration of X. Okay. Okay. So for the Brownian motion, we have a very powerful feature, namely that the increments, the future increments of the Brownian motion are independent from the natural filtration of the path. Right? So okay, let me make this precise, and this was maybe a bit vague, the statement, which is in this vague form a bit unclear. So what I want to say is that the Brownian motion is a Markov process. Brownian motion T has, and okay, several Markov properties, the simple or more general one. So it's a Markov process. Here we have the simple Markov property is enough. Property. So actually, we don't need to be precise here what this means. What I actually only need in this course, particular, if I look at the increment from the Brownian motion from B S, also from T to S, this is independent of the natural filtration of the Brownian motion up to time S. Right? This follows basically by the independent increments when one needs to show it. But here I just give it to you as a fact. This holds for all S T such when S. If you want to see the proof for it, please visit the course Wahrscheinlichkeitstheorie 1. All right, so this is, so what you should keep in mind for the course is actually this property, but we need to modify it a bit in the next video to have all the desired properties of our underlying filtration. All right, let me stop here.